All right, so we're going to talk about identifiers. So when we name things in Java, that's going to be the identifier. And identifiers can be any character, letters, digits, underscore, and the dollar sign. We have to start with the underscore, dollar sign, or a letter. You cannot start an identifier with a digit. The identifiers cannot be any word that's reserved within Java. And in the appendix of the book, it has the Java keywords, but also when we type in Eclipse, the Java keywords get highlighted a different color. So there's color coding within Eclipse that helps us keep from reusing identifiers in our identifiers that are Java keywords. They also can't be the words true, false, or null, because we're going to use those when we need to set true or false values to a logical variable, and null is a way of setting something as empty. They can be any length. They can be any length. There's no limitation to the numbers of letters they can be. Now, one of the things we use are variables. So in this computer program, the identifier radius equal 1.0. Radius is the variable, and the variable radius identifies a memory space that we can put values into. And so in this, if we look at this program particularly, it puts 1 into radius. It calculates the area using the value that's stored in radius, and the radius is the identifier that relates to what's in the memory space here. And it takes that result and stores it in the variable area, and the identifier area references that memory space. It prints out the result before, and then it comes back, and the same memory space, because the identifier radius points back to it, has a value of 2 put in it. That's going to replace the value of 1 that's in it. The calculation is run again and put into area. So these identifiers identify what Java has set up as being a memory space for variables. And we do this by declaring variables. So at the top of the program, I initialized my variables, or I declared my variables. So here, this line is saying that we're going to have this identifier x, and the memory space is going to be such that it's a type that's called an integer. We have a identifier radius, and the memory space is going to be such that it's a double, which is a particular form of decimal. And then in this, the identifier a is a memory space that gets set aside for a type of a character. And we can assign values into variables using their identifier and the equal sign operator. And the equal sign operator takes what's on the right-hand side and moves it into the memory space that is pointed to by the identifier. So here we have an integer that goes into the variable, the memory space, or the variable x. And an integer can only be counting numbers 1, 2, 3, 4, -1, -2. It can't be decimals. Now the double for radius can take this 1.0 and it gets put into this memory space. And the character A gets put into the memory space that the identifier A points to. Now notice we've been using strings. When we've used strings, we've used double quotes. Here we're doing a single character, and single characters use a single quote. Now, I can declare and initialize variables in one step. I personally say this is probably, I don't want to say it's bad coding practice. It's a good place if there's certain things that need initialized at the beginning of the program. The way I was taught and the way I scope things is I declare all the variables first, and then if I need to initialize them for as the program runs, I do that at the top of the program. This is fine programming style to initialize and declare at once, but I would recommend that you try declaring in a very, very top section of the initialization, and then if you need to put starting values into the variable, do that in the next section of your code. It won't slow down your code, and it helps with legibility. And then we can also have named constants. Now, named constants get this extra thing, this final on it. Whoops, didn't mean to hit that. And final says that the value that we're going to assign this data type with the identifier, a constant name, whatever value we put in that will be locked for the entire run of the program. And so here we're making a double called pi, and we're putting in the value of pi that we want. Here we have a final, which is an integer of size 3. By convention, when we name constants, we want to name them all capital letters. And so when we go to name things for variables and methods, and we'll learn methods in further chapters, use all lowercase letters. If you need to have multiple words to make the identifier more legible for yourself, start the second word with a capital letter and don't put any spaces in it. For class names, we capitalize the first letter and put multiple words, we capitalize each letter of a new word. Again, this makes it more human readable, and by the convention of the first letter, we know if we're talking about a class, a variable, or a method. For constants, we're going to capitalize all of the letters, and since we can't do this trick of having a capital letter for the next word, we are going to use an underscore. So let's update our code, and I'll come over here back to Eclipse, and I'm going to go back to my compute area. Now, if this was a program that I had more sections for, I might have the value of pi in many different places. And so every time I'd have to type in the number. Well, if for some reason I needed a better value of pi, so let's say I needed 3 more decimal places, and I needed the value of 3.15265. Everywhere I used pi in the code, I'd have to go in and update that number. So it's better for us to do a final double pi and have it equal the value that we're going to use in the rest of our code. And so down here, instead of using this typed in value, I'll use pi. That means later on, or if my code is large and I use pi in multiple places, if I need to change how many digits I have, I only have to do it in one place. But the program will run as if this number is in here. It won't, in a lot of compiled languages, it actually won't create memory space for it. The compiler, when it compiles the code, will replace every time it sees pi with this constant number. So if I run this here, and I enter my circle, we see I get a couple extra digits because I added digits to pi, but it doesn't change the overall running of the program. Now, there are different numerical data types. Byte is 8 bits for storage signed. And what that means is one of the bits determines if it's plus or minus. So I come over here. I'm having a problem with my mouse for a second here. Let me come over here. If I have the number of bits, they numerically represent values. So if we look at a byte, sorry, I'm using my mouse to draw because my tablet is going to my secondary monitor right now. So bear with me here. An 8-bit number, let me see if I can draw 8. There's 2, 3, 4, 5, 6, 7, 8. each digit represents something that's happening with a number. Now, for a signed byte, this is either plus or minus based off of the value in here. But each value in here can only have a 0 or 1. So this first area covers the base of 2 to the 0, 2 to the first, 2 to the second, 2 cubed. Sorry, I have to use my mouse here. I will get my tablet fixed. 2 to the fourth, 2 to the fifth, and 2 to the sixth. Now, if I have ones in all of these, and I believe the sign digit 1 will make it negative. Think mathematically, and scroll over. Negative numbers. I'll have to look at my sign bit. I haven't played with this much. This number of all ones is going to have the value of 2 to the 6th plus 2 to the 5th, and so on. Each place holds a power of 2. And so 2 to the 0th is 1. 2 to the first is 2. 2 squared is 4. 2 cubed is 8. 2 to the fourth is 16. 2 to the fifth is 32. And 2 to the sixth is 64. And so if I add all of these up, I get 127. And that's reflective here. This is going to be able to give me the number negative 128 to positive 127. And so signed integers work on the scale of, or signed bytes have that range of numbers they can represent. If anyone has ever worked with MIDI, which is a programming for keyboards and for sending data in keyboards, MIDI is unsigned, so it gets an extra bit. It has the value from 0 to 255. And so any data that your keyboard sends through a MIDI cable sends a value for between 0 and 255. Well, 0 to 255 doesn't give too much mathematics, so a 16-bit signed integer can give numbers from negative 32768 to positive 32767. 32-bit, this increases to negative 2 to the 31st to positive 2 to the 31st. And if we notice, the number gets larger. A long has 64 bits, and it goes from, I can't even read this without the commas, but it's negative 2 to the 63rd to positive 2 to the 63rd minus 1. And so this number is the range we can store in long. Now notice these are without decimals. Now, back when I worked for IBM, I had worked with some clients that had Microsoft ASPX, and there was a change to ASPX going from 32-bit to 64-bit. When I moved back to the States, I actually overpaid my Verizon bill. So in my Verizon bill on the database, it was like negative $17 because I had overpaid, so I didn't owe money. But Verizon wasn't translating that from the 32-bit it was stored in the database to the 64-bit that it was stored in that ASPX was showing. So the bit that was showing the sign of the data, the negative sign, was causing it to be a larger number. And so I took a screenshot of what the ASPX showed me as as a bill, because I ended up calling their support and asking them to take care of it here. Let me pull up this screenshot I did. Two seconds here. My drive is doing something odd on me here. I'm going to open it up. There we go. That's why. 1 second, when I open the web browser, I had to find it here. And let me see if I can switch over to it here. Oh, that's me. I apologize for this. Let me change this. You don't want to see me. I haven't shaved today. I'm going to do that later. Let me switch this over to my web browser. And there's the web browser here. So this is the image that I took of what Verizon was billing me. And so if we look here, let's see, thousands, millions, billions, trillions, quadrillions, quintillions, sextillions, septillions, octillion. So this is 79 octillion, 228 septillion, 162 sextillion, 514 quintillion, 264 quadrillion, $300 billion. And the reason I point this out, that I called and talked to their support. It took a while because I had worked on this particular technology in the background. I could explain to them, hey, your database has your data stored with 1 bit value, but your ASPX is showing it in a different bit value. And was it 32-bit? Let me pull back here. Let's see. 1, 2, 3. Yeah, it was. I'm pretty sure it was a 32-bit to 64-bit conversion. And so when we talk about these types and what we're doing with these, I think it's important to note that we have to realize that the numbers that we have will have some limitations. And if we need the numbers to be small and compact in memory, we will use the bytes and the shorts. But if we need numbers that could count very, very large, then we need the longs. There's a program where we will do the population of the United States, and if we look at an integer, this integer goes to about 2 billion. And if you do a projection of the population forward on an exponential curve, some people would run the program and they'd start getting negative results because they ran the program too far past what the number can handle. So these limitations are worth being aware of. Now for decimals, we have floats, which do negative 3.4 blah 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 times 10 to the 38th to 1.4 times 10 to the negative 45th. So these are fairly large numbers that we can do with scientific notation. A double has 64 bits, and it can do decimals from negative 1.7976 times 10 to the 308th, or times 10 to the negative 4.9. So it can do really, really large numbers with the 10 to the 308th. I'm sorry, this is 4.9 times 10 to the negative 324, or really small numbers, because scientific notation 10 to the negative 324 is a small decimal. And we can actually see, I'm going to jump back over to my program here. And one of the nice things about the libraries in Java is I can do scientific notation. So let's say I want my circle radius to be 1.2 times 10 to the third. So I'll write this in engineering notation, 1.2 e to the 3. And so this translates as 1.2 times 10 to the third, which is 1,200. And so if I hit enter, Java takes this as a number because it's written in proper notation, translates it to 1,200, and completes the calculation with it. So we're able to use these large types with our keyboard entry on our keyboard entry programs. And I'm going to stop here, put this up, and then we'll talk about the different numbers we can read from the keyboard and look at input. Just important when you declare a variable to make sure it has the type and the function you need, because as we look at mathematical operations, there's going to be some differences between integers and doubles. It's very hard for a computer to represent a decimal number. Floats and doubles work very peculiarly in the computer, and we're going to run a program that's going to show us some of these peculiarities. And so if we're counting things, we definitely want to use the byte, short, integer, long, the integers. If we're doing calculations where we need decimal points, then we want to use float and double. And so it's really important to think of that as we're declaring our variables.